Good morning, evening, everyone, wherever you are on this planet. My name is Sade Lewis, and today I'm going to walk through how we can use ArcGIS as a powerful tool to operate data science. Okay, so when people think of data science, they often imagine like machine learning, Python, spreadsheets, things like that. But in GIS, it's important because now that information is conglomerated and placed on a map so you can visually see it. Okay, so we're going from ones and zeros to complex forms of information. Okay, where that data can be stored on a map. Okay, and for that visual, we can action items. All right, so it connects geography, and geography is also is often the missing piece in understanding real world problems. Okay, so exactly where these things are occurring and why they're occurring, what other things are surrounding it. Then we get into scrubbing data, data checking, because how open science works is that people are collecting information based off of their research purposes. However, we might not need all that data. Okay, someone may be collecting the salt quantity of a specific spring. Okay, so it shouldn't really be salt there, but they're collecting salt from that specific spring. However, maybe your research focuses on the temperature, so they're collecting the temperature, the salt content, the date time group, the some other factors. So that's where data scrubbing becomes important, and error checking. So we will cover some main areas today: data cleaning using error checker, importing and exporting metadata, understanding metadata standards, building and running geoprocessing modules or models as well, a small basic routine for coordinate input. So this is where your language model is important, your program that you're using to process this information. So this is using a computer to do your calculations and telling your computer what calculations to do and where to put that information so it can be used effectively. And finally, we'll cover a real world example using deep learning to detect trees on the university's campus. And so this one is specifically for the assignment, the final assignment rubric. So my focus is water. However, I'm going to ensure that I hit these points. Okay, so for number one, data cleaning and error checker. We're going to start with the most important parts of data science, which is cleaning the data. What I mentioned earlier about large amounts of information, you don't need all those things. However, some of that information is needed. You're just figuring out what you need to take out. So your program, your app, your module can run effectively because you don't need additional data that doesn't add to the information that you're using to pull your point across. So in ArcGIS Pro, there is a tool called the Error Inspector and Error Checker inside topology that validates workflows. Okay, so the validation of the workflow is making sure that the workflow works properly. Okay, so we can set up something that looks good, but we have to make sure it flows properly and it's giving us our outputs that we are requesting. When working with spatial data, errors can include overlapping polygons, gaps between boundaries, invalid geometry, duplicate features. And to use the error checker, you want to load your feature class, point size, and polygons into ArcGIS Pro, create or enable a topology in the Geo database, okay? The Geo database, because this, again, is open science, and this needs to be available to other people. Add rules such as do not overlap or must not have gaps, and run validate topology. Open the error inspector pane. From here, ArcGIS flags each error. You can zoom to the error, you can fix it manually, or you can mark it as an exception if it's valid in context. Okay, so there might be something that you might need to stay on your map for a specific reason that's coming up as error. You can kind of like void that out as an exception to the rule. This step is essential in data science because bad spatial data leads to incorrect analysis results. Okay, think of it like a debugging, but for maps. The second portion is importing and exporting metadata, okay? This is data about data, okay? So it's getting from, the data that we collect and we see back all the way down to bits and bytes of information, so we can understand exactly where that information can flow to. And I think the metadata is like the most important portion, because where is it coming from? Where is it going? Where was it collected? How much of this? From what source was it collected from? All these things is needed for us to understand what we're dealing with when we're coming to these conclusions about data. So in ArcGIS Pro, metadata describes where data came from, how is it created, the projections it uses, when it was last updated, and how it should be used. Said previously. Import metadata, right click a data set, go to metadata and import. Choose an existing XML or metadata file, and then export the metadata. Go to the same metadata pane, select export, save as XML or another supported format. This is very important when sharing between organizations. Like I said previously, like, we are on this planet together, and we're trying to figure out the best way that the information that we collect and the conclusions that we come to, other people can use that information to come up with their conclusions and further research. Okay. Metadata standards in ArcGIS Pro. ArcGIS supports multiple metadata standards, and choosing the right one, of course, matters. The most common include the Federal Graphic Data Committee. It's an older standard, uses governmental databases, and it focuses on detailed documentation. So with any any sort of repository of information, it needs to be detailed and titled of, okay, this is for the dates, this is for the times, this is for the location, this is for what specific information is being collected, the units used to collect the information, how many significant figures is used in this information, why was it only that amount of significant figures, can we go back into, excuse me, I'm like rolling over this cover, can we go back into the data to locate exactly where the information is, because maybe we need additional significant figures to come up with a conclusion to find that very narrow point, of error. So we have the ISO 19115, ArcGIS metadata style. These are just some of the metadata standards used. So it's basically the format in which projects are information is loaded. So with working in data science, ISO is usually preferred because it's widely accepted internationally. So one great thing about math and science, of course, is a lot of different cultures and I was going to say religions, but cultures and languages can use that information. So metadata ensures reproducibility, transparency, and data credibility. Without metadata, data sets become difficult to trust or reuse. Okay. The next one is model builder and geoprocessing workflows. So the model builder allows us to visually design workflows for spatial analysis. And a typical model might include like the input. So these are feature classes that you input, your point size and polygons used for data. And then you have an output on what you want to be displayed, okay? You have a buffer tool, you have a clip tool, and an intersect tool. To build a model, you want to open up your model builder, drag in tools from the geoprocessing toolbox, okay? So you gotta put your tools in your toolbox that you want to use when it comes to your model builder. Connect them with in a logical sequence, set the parameters for user input, and validate and run the model. So validating the model is ensuring it works properly, okay, before this is published and made available to other people. While working on a workflow, a model builder. It's not accessible to people. However, once it's like published and finished, it still can be worked through based off of who the originator is, but you want to make sure it works properly so someone else can use that information. And of course, whoever the originator is, being able to have your information accessible for people to ask questions about it. Once created, models can be shared, reused, converted into Python scripts. This is extremely powerful for data science because it turns repetitive analysis into automated workflows. Another section is small basic routine for reading map coordinates. So I have this here, but I actually wanted to use a different model. Yeah, let's skip over that one because this is just using a computer language, programming language, small basic, to teach the machine spatial thinking and understanding these data sets, GIS data sets. So deep learning is when we get into the tree detection on campus. Finally, the most exciting of whatever. In ArcGIS Pro, we use deep learning tools to detect objects like trees from imagery. For example, on NCCU campus, we could use aerial or drone imagery, train a model to identify tree canopies. So these things could look like when it comes to what sensors are on whatever type of vehicle is being used. In this case, it will be a drone, an aerial drone, and we would be able to identify exactly where trees are located versus other vegetation. And so those canopies could be identified with we're going green, the bands for green, as well as infrared, which show when the sun goes down. There's still a luminance on tree canopies, and that's also affected by the quantity of water. It's more luminous after rain, so we also have to take that into accountability. The workflows include collecting labeled training data, so trees being marked on the imagery. So once we are able to ingest that information, add in additional imagery on top of that, so like symbols to identify, okay, hey, these are the trees that we map in relation to the school and how close they are, how far away they are, things of that nature. You can also train a deep learning model, such as like a neural network. And so I was digging into that a little bit. I almost didn't want to mention it because that's like another tangent I would have to go on as far as learning and also teaching what I've learned. And generate output features of tree locations. So basically, once you've already ingested that data and you understand where they are co-located on the map, you can thus create another layer of that map, identifying exactly where those trees are. And that layering could be used as, like, say for example, someone already collected the aerial view of North Carolina Central University's campus, and you want to use that data to map out where the trees are. You can create another layer. You can run your program for it to identify exactly where the trees are. To hopefully my computer does not shut down. It's trying to die, and I'm almost done with this, so I don't want to. Oh goodness. Okay, my apologies for that. So yeah, you're identifying exactly where those trees are and modeling it as a symbol, and so those symbols can now become a layer, and that layer can be used for further analysis of exactly what trees are, and that way places, organizations like Keep Durham Beautiful, or Plant a Tree. There's organizations that surround increasing the vegetation in the area and green spaces, and so that could be a talking point, because now you have actual data to support where trees are located, and attach that to additional research about the benefits of having loads of trees in our respiratory system. So in closing, we explored a few things, which data cleaning, the reasons why we do it, how we do it, the process to start to get that set up, metadata management and standards, the reason why there's standards, the reason why standards are created, and the reach it has when it comes to open science, as well as workflow automation using Model Builder, simple programming with Small Basic. We touched on that. I didn't go through the details of Small Basic. I probably can make an additional video, but this one is coming close on that time. And then some deep learning when it comes to AI-driven analysis. So thank you for your time today. I pray that we're able to assist others as well as the planet in getting things back in order. The water needs us, the planet needs us, the people need us. And so therefore we have to do the best that we can to research, find, and locate solutions that benefit the collective. So anyway, again, my name is Sade Lewis, a graduate student here at North Carolina Central University in the Environmental, Earth, and Geospatial Sciences Department.